In this video, we're going to start talking about pH titration curves. And if you've had lab before, which I'm sure you have, you've probably have done a titration, right? Our titration is where we had a burette, right? Our burette was that device that we used to measure the amount of substance or the amount of solution that we're adding to something. And of course, I'm a horrible drawer here, so this is a burette. In our burette, we have a solution called a titrant. That titrant can either be an acid or a base. So the titrant is the solution that goes into that burette. And then we had usually an Erlenmeyer flask, some sort of container, right? And then in that container, we had another solution. So this is supposed to be an Erlenmeyer flask. Sorry, that's a horrible drawing. This one I actually don't have a special name for. I just usually call it the solution in the flask. A lot of times it's going to be an acid. It could be a base. If it's an acid in the flask, then my titrant would be a base. Remember, we're always going to react acids and bases together, never two acids, never two bases. So our titration, kind of the way you would have done it in lab in the past, is you would have known the concentration of our titrant. It would be a solution of known concentration. You wouldn't have known the concentration of my acid, right, my solution in my flask. And then based on the volume and concentration of base, right, of my titrant needed to neutralize my acid, and we know the volume for that one, we can calculate the concentration of that acid. What our titration curve is going to be a graph of this. How does my pH change as base is added in this case? So this is going to be a plot, so a graph of pH versus volume of titrant. So in this case, the way I have it set up, and we're measuring this pH of the solution in the flask. So we're actually going to start out acidic. And then as I add more and more of my titrant to it, right, as I add more and more base to it, my solution is going to steadily become more basic, less acidic. I have pH on my y-axis. And then in this case, it's going to be volume of base on my x, because that's what my titrant is. And then again, we're going to start out acidic. So we're going to start out down here, right, with a low pH. And then we're going to increase gradually. At some point we make a bigger jump, and then we kind of level off again. So this is what a typical titration curve would look like. If we wanted to start out in reverse, if I started out with, and this is going to get even messier because I'm going to draw it faster. If I had acid for my titrant, so that's in my burette, and I had base in my Erlenmeyer flask, right? This time, again, pH is increasing. This time, volume of acid, right? It's always titrant here, so acid is my titrant. Because I'm starting out with a base, we're going to actually start out with a large pH. And then as we add acid to it, our pH is going to drop down. I just want to draw that a little nicer. So it could go either way. Kind of the more typical way, and the way you've probably done it in the past, is this first version where you have acid in your flask, base in your burette. We're starting out acidic, and then our pH becomes more basic as we go. We will look at this scenario also though. So if you see a pH titration curve where it's starting out basic, right? Starting out with a high pH, that means we're starting out with a base, we're adding acid to it, so my pH is decreasing as the reaction proceeds. I do want to define what's called our equivalence point. We're going to be using that term quite a bit. And our equivalence point is a point at which a stoichiometric equivalent amount of acid and base has been added. So essentially what that means is the moles of acid are equal to my moles of base. So the point at which a stoichiometric equivalent amount of acid and base have been added, which is just our fancy way of saying that the moles of acid are equal to our moles of base. And then our pH at that equivalence point is going to vary depending on whether I have a strong acid, strong base titration, a strong acid, weak base, a weak base, strong acid, or if they're both weak, right? The equivalence point, my pH can change. If they're both strong, it's actually going to be a neutral solution at that point. So we're going to start with a strong acid, strong base titration. And for all of these, I think the easiest way to go do it is to just go through an example and kind of talk about it as we work through the problem. So our first one, a strong acid, strong base titration. So my acid is going to be in my flask, my base is going to be my titrant, it's going to be in my burette. We're going to start out acidic, we're going to add more and more base to it until we're basic. And then our problem, we're going to have 40.00 milliliters of a 0.100 molar hydrochloric acid solution is titrated with 0.1 molar, 0.100 molar sodium hydroxide. So hydrochloric acid is a strong acid, sodium hydroxide is a strong base. And a couple things we're going to calculate. Our first one is we're actually going to calculate the volume of sodium hydroxide needed to reach the equivalence point. We don't actually need this to be able to calculate the pHs, but as we go through kind of more problems, more complicated ones, it's going to be kind of a good number to have. It's going to allow us to make a couple shortcuts, particularly for the weak acid and weak base ones. So even if the problem doesn't ask for this, I would always calculate this because again, it's just a number you want to have because it's going to be useful. So we're going to calculate the volume of sodium hydroxide needed to reach the equivalence point. Remember, the equivalence point is when my moles of acid are equal to my moles of base. So we're going to determine how many moles of acid we have, right? We know that this is moles per liter. I have a volume, so we can calculate moles. And then we're going to set that equal to my moles of sodium hydroxide, right? At the equivalence point, moles of acid are equal to moles of base. And then using its concentration, we can figure out the volume. I am going to use millimoles. If you don't want to, you don't need to, but it's going to make your life, like you're going to save two calculations like per step if you use millimoles. So just kind of a side note here. If I look at molarity, right, capital M, that's equal to moles per liter. It's also equal to millimoles per milliliter, right? If I was to take 10 to the negative third on the top times moles, right? 10 to the negative third is milli, and then 10 to the negative third on the bottom times liters, that gets me milliliters. Those 10 to the negative thirds cancel. So molar is the same thing as millimoles per milliliter. And you can use any metric system if you want. We could do gigamoles per gigaliter, right? You would multiply the top by 1 billion, you'd multiply the bottom by 1 billion, and those billions would get canceled out. So it doesn't really matter which kind of like, as long as the ratio is the same, it's still going to be molarity. So if you want to, right, if we just go back to the milli, right? If I take 10 to the negative third moles, that is millimoles, and then take 10 to the negative third liters, that is milliliter, right? Those 10 to the negative third, since one's on top and one's on the bottom, they just get canceled out. So millimoles per milliliter is the same thing as moles per liter. Nanomoles per nanoliter, centimoles per centiliter. As long as you have the same metric system prefix on the top and the bottom, they actually get canceled out. Why I want to use this is because then I don't have to convert between milliliters and liters every time I do a calculation, right? If I didn't want to use millimoles, I would have to convert this to liters, multiply it by this to get moles, then I would divide that by this to get liters, and then I would convert from liters to milliliters again. So I would have to do 2 conversions as part of the problem. By using millimoles, I don't have to convert between milliliters and liters. So essentially, instead of saying, right, my equivalence point, if we go back up here, moles of acid are equal to moles of base, I'm going to say millimoles of acid are equal to millimoles of base. And again, you could use any metric system conversion you want. Nanomoles of acid are equal to nanomoles of base. Micromoles of acid are equal to micromoles of base, right? As long as you're using the same unit on both sides, acid is equal to base, right? Moles are my amount. Scale it up, scale it down, it doesn't matter. So I'm going to use millimoles. It's going to save me 2 conversions per problem. So I would highly recommend using it also. It might be a little confusing at first, but I promise you it's going to make life better. Or quicker anyway. It won't be quite so tedious. So what I'm going to do is I have 40.00 milliliters. And then my concentration, right? I have 0.100 millimoles per milliliter. These are going to cancel. And I'm going to have 4.00 millimoles of acid, right? I just took my concentration, I multiplied it by my volume. By keeping this in milliliters, this comes out in terms of millimoles. Because I'm at my equivalence point, right? I'm trying to calculate the volume at the equivalence point. I need 4.00 millimoles of sodium hydroxide, right, at the equivalence point. Because moles of acid are equal to moles of base, in this case millimoles, but it's really the same thing. My problem wants volume, so now I'm going to use the concentration of sodium hydroxide. So 4.00 millimoles. This time we need to divide by that concentration, so that way millimoles cancel. And we're going to end up with 40.00 milliliters of sodium hydroxide needed. If your concentration of your acid and the base are the same, right, they're not always, but if your concentration is the same, so in this problem it is 0.1 molar each, then the volume at the equivalence point is going to be the same. The concentration is not always going to be the same though. So don't just assume that it's going to be the same volume. That only works when the concentrations are the same. So the volume of sodium hydroxide needed to reach the equivalence point, 40 milliliters. Kind of the way that I'm going to do this problem in the future is I'm going to write it a little bit shorter. I'm actually not going to write out millimoles per milliliter. I'm just going to take 40, multiply it by the 0.1 to get millimoles, and then divide that answer by the concentration of my base to get milliliters. And again, if this confuses you, by all means, convert between milliliters and liters every time. I just really think after you do a few of these, you're going to like this method because it's saving 2 calculations each time. Okay, so now that I have that number, right, I know that I need to add 40 milliliters from my burette into my flask to reach that equivalence point. So we're now going to calculate the pH of the solution after, and then we're going to have different points. So the first one, just initially, we could say after 0 milliliters of base has been added. So essentially what I have is just, if we go back up here, just this acid solution, right? We've added no base to it. I just have 40 milliliters of a 0.1 molar hydrochloric acid solution sitting in my Erlenmeyer flask. We want to know what its pH is. We do know from chapter 14 that if I have a strong acid, my strong acid concentration is my hydronium ion concentration, right? And this is only when it's strong, since a strong acid. So what that means for us is that our hydronium ion concentration is 0.100 molar, and then my pH is simply going to be the negative log of that number. So my pH comes out to be 1.000. Right, watch those significant digits. This is 3 significant digits. My pH is a log value, so only the digits after the decimal point count. So 1, 2, 3, that is 3 significant digits. So when that acid is sitting in the flask, we haven't added any base to it. So initially, right, 0 milliliters of base have been added. The pH of that solution is 1.000. So just kind of a note to ourselves. We're going to calculate it as you would. For any strong acid. Our second point is we're going to calculate the pH after we've added some base, but before the equivalence point. So for this one, let's calculate it after 10 milliliters of sodium hydroxide has been added. So kind of our directions, right? They're in 2 different spots. Calculate the pH of the solution after 10 milliliters of sodium hydroxide has been added. So that base that we're adding is going to neutralize some of our acid, right? Those are going to undergo an acid-base neutralization reaction. So we're going to write that neutralization reaction. So, and I'm just going to write it as my net ionic equation. right? My strong acid, HCl, is H3O+. Right? We've gone through this a few times, but remember, it's completely dissociated. I'm not going to care about this, and then protons in water are actually hydronium ions. So if you have a strong acid, I'm just going to think of it as H3O+. I don't care about the rest of it. So just kind of in your head, strong acid, H3O+. Those two are always going to be equivalent for us. And then my strong base, I have sodium ions, which are not going to react. They're inert. We don't care about them in terms of this reaction. And I have hydroxide ions. So again, if you have a strong base, right, just think of it as hydroxide. So my neutralization reaction between my strong acid and my weak base, my strong acid and my strong base, is going to be this. We're going to now make a change table, essentially, right? I'm going to start it with my original concentrations, and we're actually going to use amount. We're not going to, we're going to no longer ignore volume changes. So I'm actually going to talk about the amount that I have versus the concentration. So the number of moles. Remember, moles was our SI unit for amount. I'm going to use millimoles, and that's going to work just fine. We're going to look to see how it changes, right? Some of that base is going to neutralize some of my acid. I'm going to then figure out my new amounts, my new number of moles, and then we're going to turn those into concentrations and figure out our pH. So I'll kind of write the steps after, but step one, write our neutralization reaction. We're going to make a change table, but we're going to use moles or millimoles instead of using molarity, right? Instead of using concentration. So I'm going to have my initial number of moles. And again, I'm going to use millimoles. If you want to convert between milliliters and liters every time, go for it. I'm not going to. I'm going to have my change, and then I'm going to have my new number of moles. Be really careful. What we did before is we put brackets around stuff, but that meant concentration. I'm not using concentration anymore. I'm using moles, right? Those terms, those brackets are molar concentration. I'm not doing moles per liter or millimoles per milliliter when I make this change table. I'm doing the number of moles or the number of millimoles. So the number of millimoles of acid, we already figured that out up here, right? If I'm starting out with 40 milliliters, right, that's just coming from the problem, and its concentration is 0.1 molar, I have 4 millimoles of hydrochloric acid in that solution. So this is 4.00 millimoles. And again, if you want to convert your volume to liters and use moles every time, you can. That's fine. We're going to get the same answer in the end. I'm just going to move this over a little bit. To figure out the base that I added, right, we need that number yet. I've added 10 milliliters. Its concentration, going back up, is 0.1 molar. So if I take, just kind of over here on the side, if I take my 10 milliliters and I multiply it by my 0.100 millimoles per milliliter, I'm going to have 1.00 millimoles of my base, right? This is my base. So that's the number that's going to go into my table here. And then water doesn't, right? We can talk about amount, I guess. You could just say 0 there because I'm not starting out with any. And then remember, just like we were doing with our buffer solutions, this isn't a buffer, but it's the same sort of idea, right? It's a limiting reactant problem. I have 2 reactants, right? It can never proceed further than the one that I have less of. So we're going to take the one that I have less of, and I'm going to subtract it from both. And then all of this base has been neutralized, and I have 3.00 millimoles of acid left over. So I have excess acid at this point. which makes sense, right? I started out with acid. It's before the equivalence point, so moles of base are not equal to acid yet, right? I have less of it, which means I'm going to have excess acid. I do still have to figure out my pH. Remember, my pH is the negative log of my hydronium ion concentration. This is not my concentration, right? This is my amount. So I do need to divide that by my total volume. So I'm going to take the number of millimoles that I have. I'm going to divide it by my total volume in liters. So I'm starting out with 40 milliliters of acid, right? That's what's in my Erlenmeyer flask. I've added 10 milliliters from the burette to that acid in the flask. So that means I actually have 50 milliliters in that flask right now, right? We started out with 40 of acid. We added 10 milliliters to it. So 3 divided by 50, I have 0.0600 molar hydronium ions. So again, just be really careful, because I'm using millimoles, I can just divide by milliliters, right? Millimoles over milliliters gives me my molarity. If you're using moles here, then you need to convert these volumes to liters, because moles divided by liters gives you your molarity. So again, if you don't like the milli version, you don't have to use it. Just make sure that you're converting between milliliters and liters every time. I still have to get my pH. My pH is then going to be the negative log of my hydronium ion concentration. So I'm just typing that into my calculator. And I got 1.222. So again, watch those significant digits. There's 3 significant digits here. This leading 0 doesn't count. So I want 3 digits after my decimal point. And then just make sure it makes sense, right? We've added base to it. So my pH needs to be more basic than I started out with. So I started out with 1. Oops. I started out with 1. This is more basic than that number, so good. If it came out less than 1, we goofed up somewhere, so go back and check. So just kind of looking at those steps again. We're going to write our neutralization reaction. In these first 2 steps, you can do whatever order you want. You're going to figure out the number of millimoles of base that you added. You're then going to make a change table, subtracting the smaller of the 2 reactants from both reactants. That's going to give me my new number of millimoles of acid. pH is the negative log of the concentration, so you then need to divide it by the volume to convert it back to the concentration. Then you can take the negative log of that to get the pH. So again, kind of the new trick to this that we weren't doing before is we're no longer ignoring the fact that our volume is changing. So we need to plug moles or millimoles into our change table and then turn it into our concentration after by dividing through by the total volume, right? This is my total volume. Our next one, we're going to calculate the pH after 40 milliliters of base. I'm just writing down the concentration here, has been added. Right, that number, this one I didn't write it down, but it was a less of a scroll, right? It is given in the problem up here. So this one, I can, if I recognize, right, if I did that first calculation, I recognize that this is my equivalence point, right? If we go back up to that very first question we were asked, right, we wanted to calculate the volume of sodium hydroxide needed to reach the equivalence point. It was 40 milliliters. 40 milliliters. So I know this is my equivalence point. So if your concentration of strong acid is equal to your concentration of strong base, right, and you've added the same volume, so your moles of acid are equal to your moles of base, what is your pH at the equivalence point if they're both strong? Yeah, it's going to be 7. And you could just write that. You don't even have to actually do any math here. If you recognize this is the equivalence point, my pH is going to be 7.00. And again, this is only for strong acids, strong bases. Do you pay attention to this heading here, right? Our pH is not going to be 7 if I have a weak acid and a strong base. It's going to be greater than 7. If I have a strong acid and a weak base, it's actually going to be less than 7. So do be careful. If they're both strong and I give you a volume, that's the volume at the equivalence point, you can just tell me the pH is equal to 7 without doing any other work. You could just leave it like this, and I would be totally cool with that. If you don't recognize that as the equivalence point, make your neutralization reaction, make your change table, plugging in your number of millimoles, and then look to see what you have. So I'm gonna do that just so you can get practice doing these steps. I think we need practice doing them, so I'm gonna do it. So let's say I didn't realize that this was the equivalence point. I didn't do that first calculation, so I didn't know that 40 milliliters was the equivalence point. So I'm gonna write that change table. My acid is reacting with my base. I'm forming my 2 water molecules. I know initially I have 4 millimoles of my acid, right? We started out with 40 millimoles of a 0.1 molar solution. Calculating my millimoles of base, right? We're going to do it just like we did up here. I'm going to take my volume and multiply it by its concentration. So for my base, I have 40 milliliters multiplied by 0.100 millimoles per milliliter. Milliliters will cancel, and I'm going to be left with 4 millimoles of my base. So that's the number that's going to go into my table. I'm going to look at those. I'm going to subtract the smaller of the two numbers from both of them. They happen to be the same. So I'm going to subtract 4 from both, which means this goes to 0, this goes to 0, and the only thing I have at this point is water. We know that water reacts with water to go in the other direction to form hydronium ions and hydroxide ions. So those two multiplied by each other is equal to 1.0 times 10 to the negative 14th. And then using some math, that tells me that the concentration of each is 1.0 times 10 to the negative 7th. You take the negative log of that. This is all stuff we've done before, and I get a pH of 7. So all of my acid has been neutralized by all of my base. Both of those go to 0. All I have is pure water. My pH of pure water is 7.00. Part D. We're going to calculate the pH after 60 milliliters of my 0.1 molar sodium hydroxide has been added. So same thing, we're going to write our neutralization reaction, we're going to make our change table, we're going to subtract the smaller of the two reactants from both of them, we're going to look to see what we have. We do need to calculate the millimoles of base that we've added. So at this time I have 60 milliliters times 0.100 millimoles per milliliter, which gives me 6 milliliters of base added. right? I didn't write I've added here, but this is what we've added at this point. Same for all three of them, right? Added. So writing my neutralization reaction, my acid plus my base, going to 2 water, and then my original number of millimoles, this was 4. This time I've added 6 millimoles of base. Oop, forgot an M. Always take the smaller of those two numbers, subtract that from both sides. So this time 4 is my smaller number. So all of my acid has been neutralized, and I have 2 millimoles of base left over. So what we have at this point is excess base. And it's strong base, excess strong base. So we're going to calculate the pH like you would for any strong base solution, right? We need to figure out the concentration of hydroxide ions. Then you can either figure out the pOH and subtract from 14, or you can divide it into kW to get the hydronium ion concentration and take the negative log of that. Again, I do need concentration, however, so I need to divide my 2 millimoles by my total volume, right? Concentration is millimoles over milliliters. So we started out with 40 milliliters, right? That was in our flask to begin with. I've added 60 milliliters from the burette to it. So I actually have 100 milliliters total. So I have a 0.0200 molar hydroxide ion concentration, right? This equals my concentration of hydroxide ions. So again, don't forget, we're not ignoring that volume change anymore. That's a really easy thing to do because we've been ignoring volume changes for a little while now, but we're not going to do that. So I'm starting out with 40 milliliters of acid. I've added 60 milliliters of base to it, so I now have 100 milliliters total. So we take the number of millimoles of base that I have, we divide it by the total volume in milliliters, and then that gets me my concentration. Again, if you want to be using moles and liters instead of millimoles and milliliters, that's fine. Just don't forget to convert every time. So I'm going to figure out my pOH and then subtract from 14. You could do it the other way if you want. So negative log of 0.02. I get 1.699. And then 14.00 minus 1.699. I get a pH of 12.30. So it is now basic, right? I have excess strong base. I'm getting a basic pH. I do want to look at the graph for this and then just kind of look at it again a little closely. So if I look at my curve, right, I have pH increasing. That's a horrible arrow. And then I have the volume of base increasing left to right on my x-axis. And then we're starting out acidic, right? If we look at our numbers here, the first pH we calculated was 1. So that's my pH before I added any base. So if I was to draw a curve here, that's pretty ugly. Let's try that a little better. Right at this point, if this is 0 milliliters of base, my pH was 1.000, right? My equivalence point, if we look at our graph, it's actually the point of inflection. So it's where the graph kind of stops going up and starts going back. If you were to kind of like eyeball it, guess where it is, it's really in the center of that straight part. Kind of the easier way to do it is if you were to take, let me just draw this a little bit better so we can make it look good. I'm just going to make this a little bit longer. And it's not much better, but it kind of, see how it kind of levels off. So if you were to try to draw a straight line, kind of where it levels off, and then like a straight line here, and then you were to like measure kind of halfway through those, that is your inflection point. That's going to be my equivalence point. The easiest way, and for us, it's accurate enough because we're just really estimating here, is this steeper part. It's like the halfway point. So that's my equivalence point. If we were to add our values on our graph, right? This was 40 milliliters of base. That's not a very good straight line. Sorry, I should have some dotted paper here. And this was a pH of 7.00. And then anything between those 2 points is going to be acidic. I'm going to have excess acid. So everything between this initial and this line is not straight. It really bothers me. Sorry. It's probably not going to be straighter, but I'm going to try a little bit better. That's slightly straighter, which means we need to move this tick mark. I knew that was going to happen. Make my eraser tinier. Maybe I can do it. Okay, perfect. Okay. So what that means for us then is everything between the initial and the equivalence point, everything between here and here is going to be excess acid. Right? We're starting out with an acidic solution. I have not added enough base yet to neutralize it, so it's excess acid. If we go up to our change table, right, this one, you're always going to have everything between the initial and the equivalence point. You're going to have a bigger number for acid than you do for base. When you subtract it, you're always going to have excess acid. If we looked after the equivalence point, right, because at the equivalence point they're neutral, but after the equivalence point it's going to be excess base, right? The millimoles of base that I have are greater than the acid, right? At the equivalence point they're equal, but then we added base, right? We made them equal and then we kept adding base, so it's going to be excess. So if I go here, right after this is going to be excess base. And then at that point, right, just that point, my moles of base are going to be equal to my moles of acid. And then if it's a strong acid, strong base titration like this one, it's going to be 7. Again, this 7 over here, right, is only when they're strong. Again, this is only a strong acid, strong base example. We will do the other combinations. If we wanted to add my other numbers on here, right, scrolling back up, I had 10 milliliters of sodium hydroxide that I added. So if I have 0 here and 40 here, roughly halfway between the two would be 20. So somewhere in here would be 10. This is getting kind of messy, but let's say this is 10 milliliters. I would go up till I hit my graph, and then I would come over, it's really close, over to here, and that would be the 1.222. If you were to try to fit it in there, that would be that value. And then, 60 would be somewhere over here. I'm just estimating again. So you would go up. And then, I don't know if I made enough room. We would go over. And that would be my pH of 12.30. Again, that was horribly not straight, but you guys get the idea, I hope. So again, Initially, these are the parts I really want to make a big deal of. Initially, right, when it was 0 milliliters, it was just my strong acid. At the equivalence point, the two are equal, so everything between here and here is going to be excess acid. At this point, I've neutralized all of the acid, but I keep adding base to it, so then everything after this, right, as I keep adding more, is going to be excess base.